Okay, one more example before I get to hysteresis. So here is the next example. It says the coil in figure 3, so this is figure 3, has 250 turns. So this is a toroid that has 250 turns and is wound on silicon sheet steel. So the material of this magnetic circuit is silicon sheet steel. I don't know if you can see from the lighting here, but you know, the coil in figure 3 has 250 turns and is wound on a silicon sheet steel. Now I know you can see the next sentence. So it says the inner and outer radius of this toroid are 20 and 25 centimeters respectively, and the toroidal and this toroid has a circular cross section. So the area of this toroid is a circuit. For a coil current of 2.5 amperes, so this is 2.5 amperes, find the magnetic field, the magnetic flux density and the inductance of the coil. So we have to find the magnetic field, magnetic flux density. Because we know that this is a silicon sheet steel, we had a magnetization curve for that particular material, the BH relation, which I did in my previous videos. So first we are going to measure what is the magnetic field intensity, and there are a lot of tables on the internet and in your books that you can find the magnetization curve for silicon sheet steel. That's a commonly used material, and when we calculate the magnetic field intensity, we know what is the magnetic flux density, because I can't write down the figure, but when we calculate what is the magnetic field intensity, I'm going to look at the table in my book, and I'm gonna see what is the value of the magnetic field, magnetic flux density. So first, if you want to calculate what is the magnetic field intensity of this magnetic circuit, we have to know what is the length of the mean length of this particular magnetic circuit. So how are we going to calculate what is the magnetic mean length of this toroid? Well, if we know that from here to the radius from here to the magnetic field, the mean line, then we can calculate the circumference of this magnetic circuit if we know what is the length or the radius from this center point to the magnetic to the mean length of the toroid. So this mean length is in the center of this toroid. How do you know what is the radius of the mean radius of this magnetic circuit? Well, it's in the middle. It's between this line and this line. So what is the length from the center to the mean length? Well, you can measure it like this. So the mean radius is, how do we know? Well, if you don't know it intuitively, you can do like this: 25 plus 20. 25 plus 20 and divided by 2, you will get the radius of the mean radius of this toroid. And if you know intuitively that is between 25 and 20 centimeters, you will know that is 22.5 centimeters of the length, the radius of the mean radius of this toroid. So the mean radius is equal to 22.5 centimeters. Now, if you know the radius from here to here, and this is a circle, you can calculate the length of the core, because it is equal to the circumference of the toroid. So LC is equal to 2 pi times 22.5 centimeters. I transfer centimeters into meters. And this is equal to 1.413 meters. So the mean length of this core is equal to this. Now, if we use the Amperes Circuit Law, we know that the magnetic field intensity multiplied by the mean length of the core is equal to the MMF that is produced in this coil. Now we know that the magnetic field intensity is equal to N times I divided by LC. So that is equal to 250 times 2.5 divided by 1.413. Now that is equal to 250 2.5 divided by 1.43. 442,3 ampere turns meter. Now we know the magnetic field intensity and the magnetization curve for the silicon sheet steel goes something like this. And now, looking at the figure for 442.3 ampere turns meters, we have 1.225 Teslas. So this is something that you look in the tables or the figures of the magnetization curves. You can find it on the internet, on your book, in your literature books. You have, so when you know the magnetic field intensity of the core in your magnetic circuit, you can, and for various materials of the magnetic circuit, you can find out what is the equivalent magnetic flux density. So we have that the magnetic flux density of this core is equal to 1.225 Teslas. one more thing to know, and one useful, before we go to the inductance of, before we know what is the inductance of this coil, we should know what is the permeability of this core, because we need to calculate the reluctance of this magnetic circuit so we can measure the inductance. Now, knowing that the magnetic field density also is equal to the permeability times we know that the magnetic field intensity is equal to the let me just, okay, now the magnetic flux density of the core is equal to the permeability of the core times the magnetic field intensity. Now we can measure the permeability of this core. It is equal to the magnetic field intensity of the core divided by the magnetic flux density, and you get 400, and this be divided by this, and is equal to 361.06. And no, this isn't right, because this goes in the denominator over here. You get the permeability of the core is equal to the magnetic flux density divided by the magnetic field intensity. Sorry about this one, and 1.225 divided by 442. You get that the permeability of this core is equal to 2.769 times 10 to the minus 3. Okay, now we know what is the permeability of the core. Sorry about this one, my brain stopped for a second. Now we can measure the inductance, which is equal to number of turns divided by the reluctance of the core. Now we have the number of turns, and for this reluctance C, we're gonna measure it. Just gonna now the reluctance of this core is equal to the length, mean length of the core divided by the permeability of the core times the area of the core. Now we have the length of the core, which is equal to 1.413 meters. Now we have this permeability, which is equal to that, and we have to calculate the area of this core. Now, as you can see in the example, it says that the toroid has a circular cross section. So the area of this toroid is a circle which has a radius of, well, what is the radius? What is the length from here to here? That is easy. That is, 2.25 centimeters, because here we had here 22.5 centimeters. Minus this 20 centimeters, you get 2.25 centimeters. So the radius of this is 2.25 10 to the minus 2 centimeters. So the area of the core is equal to, when we know the radius, it is 2.25 times 10 to the minus 2, because we always have to transfer in the basic units, and the basic unit for the length is meters, not centimeters, squared times pi. So this is the area of the cross, this is the area of the core, because it says that it has a circular cross section. So if you cut here and look at it, you would have a circle which is equal to this. Now 2.25 times 10 to the minus 2 squared times pi, you get that the area of the core is equal to 1.5904 10 to the minus 3 meters squared. Now we can calculate what is the reluctance of the core, so we can calculate what is the inductance of the coil in this circuit, which is equal to 1.413. The length of the core is 1.413. The permeability is 2.769 times 10 to the minus 3 times this. And I'm gonna calculate that. And we get that the reluctance of the core is equal to 320,851 ampere turn Webers. Now the inductance L is equal to N squared. We have 250 squared divided by the reluctance of the core is equal to 320,851, and we get (0.194 Henry). That is the inductance of the coil. And just a second, it is close to this, but well, this is the value I get. Sorry, this was without a comma, the value of, or forgot to say 10 to the third. And you get 0.194 Henries. I forgot to say that this was 10 to the third, but when I calculated in the calculator, I calculated with this value, and yeah, it's kinda 0,194. That's kind of it. So thanks for watching, and see you in my next video.